Welcome to this short course on process simulation. The aim of this lecture and its accompanying tutorials is to give you a basic level of familiarity with a piece of process simulation software called UniSim. It will also give you familiarity with another piece of process simulation software called HySys, since HySys and UniSim come from a common source. We're going to start by examining why you might need to use process simulation software and then look at the various tasks that it can be used to do. Next, we're going to examine the process simulation workflow, and in doing so, we'll highlight some important pieces of information that you're going to need. We'll see that there are a number of different models and approaches to model chemical reactions, chemical reactors, and other unit operations, and the choice of which model to use depends on the task that you're doing. This course consists of 3 videos, including this one, so let's see what it is that these videos will cover. So, here on the whiteboard, I'm going to give you an overview of the 3 videos. The first, this one, is going to be a short introduction to process simulation. The second is going to be a tutorial. This tutorial concerns building a simple flow sheet for a methane steam reformer, and in that tutorial I will cover the following topics. We will talk about setting components, setting thermodynamics, and specifying chemical reactions. We will talk a little bit about things called material streams and energy streams, and we will see how they can be used to do physical property calculations. We're going to look at some simple unit operations: heaters, coolers, pumps and compressors, and then we'll talk about conversion reactors and flash separators. The final topic of tutorial 1 is going to be looking at how to recycle, and we'll see when we talk about that recycling is a non-trivial operation that should be approached with some care. The second tutorial is ideally aimed at 3rd year level, but will also be applicable to those in 2nd year as well, and we're going to be looking at a hydrocarbon distillation sequence. In this tutorial, what I'll be covering is the use of shortcut columns and how they can be used to generate initial conditions for rigorous columns. We'll talk about the default convergent state for rigorous distillation columns, and then we will examine how to converge rigorous distillation columns to different specifications, those that we might actually want, rather than those that are set as a default. We will then go on to conclude this tutorial by troubleshooting how to get distillation column sequences to work properly in a simulator. So, on with this lecture. The first thing we need to think about is what it is you're trying to achieve with your process simulation, because a process simulator can be used for a number of distinctly different jobs. The first of these jobs could be the calculation of initial steady-state heat and mass balances, typically used for flowsheet development and sometimes for sustainability studies. The key questions that you're trying to answer here are: what are the stream compositions, and roughly how much energy is used in making those stream compositions? Now, if we think about this from a flowsheet perspective, we don't need detailed unit operation design to fulfill this goal. You might wish to have approximate unit operations, but with those approximate unit operations to have some kind of crude optimization so that they're operating roughly correctly. You might also wish to include the first heat integration schemes, since that is very, very important in determining your overall energy use. So these are usually used for safety and feasibility studies, and sometimes for sustainability studies. Now, the second job you might wish to use a process simulator for is the optimization of a steady-state flowsheet. This usually presupposes that you've done the first step, and the key questions that you're trying to answer here are: what are the likely unit configurations and operating conditions, what is the safety profile of the flowsheet, and what is a crude estimate of the capital and operating cost. So again, we're looking at this simulation from a flowsheet perspective. Now you'll need to do some detailed unit operation design, because you need to have some idea of unit size and also an idea of roughly an optimized unit size. We're not looking at complete optimization here, but we want something that is roughly in the ballpark, so to speak. Now, some unit operations might require more optimization than others. For example, if you compare a reactor to a distillation column, the distillation column is easier to optimize first off, and it is likely at this point you might have progressed the optimization on those columns relatively far with respect to, say, how much you might have optimized a reactor. At this point you will have also included a fairly good heat integration scheme, because that directly affects your operating cost. And this type of flowsheet can also be used for sustainability studies and can often yield far more accurate information. It depends of the state of the sustainability study you're wishing to do. Is it a quick first pass, or is it a more detailed overview? If it's a more detailed overview, then the optimized process flowsheet is going to be what it is that you need. The third thing you might wish to do with a process simulator is do some detailed steady-state unit design. Now, this presupposes that we've done the first two steps. You've got a good idea of what your flowsheet is, you've optimized it to a greater or lesser extent. Now you're asking the question, what does this particular unit look like? It might be a chemical reactor, it might be a distillation column, it might be a flash separator, and you're trying to yield detailed design information. So the focus has shifted. We're no longer concerned about the overall flowsheet. The overall flowsheet has set some performance specifications, and now we're focusing in on the unit that delivers those specifications. So you can do this independently of the optimized flowsheet, or you can integrate it within the optimized flowsheet depending on what you wish to do. If you do it independently, you must make sure that the unit in question actually hits the performance targets that have been set by the overall flowsheet. If you're combining the unit into the flowsheet, be aware that if you change the unit configuration, then it can have quite a large impact on the remainder of your flowsheet, which may then be very difficult to reconverge. And so it's a design decision how you go about this particular task. Now, the fourth job you might wish to do with a process simulator is look at the dynamic simulation of aspects of the final design. The key questions here are somewhat different. It might be, for example, what's the transient unit behaviour or the transient plant behaviour? How do you start the plant up? How do you shut it down? How do you control certain units? What the control parameters actually work best? In order to do this step of the design, yes, you need to have done the first three stages of the design, but also you need to have progressed the unit design to completeness as well. Because now really you're assuming that the unit is going to be as configured, and you're looking at the control systems and the instrumentation systems and the dynamics associated with them. So dynamic simulation can take an order of magnitude longer to do than steady state simulation, just as a warning. So, for this particular lecture, we're going to assume that we're interested in the first of the three tasks. We're looking at the initial steady-state heat and mass balances, and we're developing a flow sheet, because we have to start somewhere, and this is a good place to start. Now, what I'd like to do is to talk through the distinct workflow that exists when you start to set up a simulation and when you start to work through the flow sheet development. There are two steps to this. Firstly is setting up the simulation environment. Let's talk a little bit more about this. Within the simulation environment, you define what chemical species are present. Hopefully these will be within one of the process simulator's databases. If not, in many simulation tools, including UniSim and HySys, you have got the option to build up chemical species using functional groups. This can be somewhat long-winded and is out of scope of this particular tutorial and lecture. However, you need to be aware that that capability exists. Once you've defined your chemical species, we move on to a really important step, which is defining how they behave. This involves setting a thermodynamic model and also some aspects of physical property calculations. This step is so important it deserves a mention all of its own. The correct choice of your thermodynamic model is absolutely crucial when it comes to process simulation. This cannot be overstated enough. The wrong choice of thermodynamic model effectively renders your simulation and the design that then stems from it completely worthless. Because if you think about what thermodynamics do, they're going to be responsible for the calculation of equilibria, amongst other things. And if you think about the operation of a lot of pieces of plant equipment, vapor-liquid and vapor-liquid-liquid equilibria are absolutely key to their performance. Think of a distillation column and the vapor-liquid equilibria that exists to affect the separation. Think about a stirred tank reactor and the vapor-liquid equilibrium that exists between the gas phase and the liquid phase, or sometimes the liquid-liquid vapor equilibrium that exists if you've got a more complex multiphase mixture. If the prediction of those equilibria are wrong, then your design is wrong. So, it's necessary to validate the predictions of your thermodynamic model before you go any further. Typically, you might look at the predicted bubble point or dew point curves for mixtures. For simple single components, you might look at boiling points. And for liquid-liquid phase equilibria, you might look at the position of the phase boundary. We need to validate the model predictions against something though, and usually this would be experimental data. That is the gold standard. However, I do recognise that since you're approaching simulation for the first time without a full chemical laboratory at your bidding, you might not have access to experimental data. So, from your standpoint, what you can do is look in the literature. There are a lot of good data-based journals. The Journal of Chemical Engineering Data is one, for example, and you will find a lot of equilibria data there. Sometimes it's not easy to find what you need, but I would encourage you to look and look thoroughly such that you can make the validation correctly. So please, please, please remember that you must at all times validate your thermodynamic model. In the first tutorial, I'm going to proceed with an unvalidated model. It's going to be validated by assumption, which is not the way to do it, and you will see firsthand what it is that goes wrong when you use an incorrect model. Okay, so what we need to remember then is once we've defined our thermodynamics, we define chemical reactions. And there are a number of ways in which you can define chemical reactions, so let's go through those. So you choose the type of chemical reaction according to your simulation aim. There are simple chemical reactions that are good for the aim that we're looking for, which is just flowsheet development. And there are more complex embodiments of chemical reactions that really are focused at specific unit design. So again, choose what you want depending on your aim. Now, if you're looking for flowsheet development, you will find the simplest chemical reaction of the lot is something called a conversion reaction. This basically says, well, if I've got A reacting with B converting to C, 90% of A converts to C, for example. If you specify a conversion reaction, it has to be used with a conversion reactor. It won't work with any of the other reactor models. Now, sometimes a conversion isn't necessarily correct. What you have is an equilibria, and you can have an equilibrium reaction. A reacting with B forms an equilibrium with C. And the data that you can give the equilibrium reaction is something along the lines of 90% of the equilibrium position is attained, and then you've got a choice of how to define the equilibrium constant. Likewise, an equilibrium reaction, much as a conversion reaction, has to be used with its own specific reactor type. So an equilibrium reaction has to be used with an equilibrium reactor. So these two reaction models are very useful for the initial steady-state heat and mass balance development of a flowsheet, because you don't need to know detailed kinetics. All you need to know is some idea of conversion or equilibrium, or the desired conversion or desired equilibrium. If you're doing unit design, you need more information, because if you're producing the mechanical design of a physical reaction system, then you need to know sizing, something about residence times, you need to know temperature profiles, you'll need to know rate data in order to design that. And so if you use the more complex reaction models, you will need to know a good degree of rate data, which may or may not be straightforward to find. There are three major rate models within UniSim. There's a simple rate model that I've put there on the whiteboard for you. There is a kinetic model, which is slightly mathematically different, which I've put there on the whiteboard for you. And the most complex is the heterogeneous catalytic model, which is an isotherm-based model, such as the one I've just put on the board for you. Now, at this point, it must be stated that these are the built-in models, these five models, these two simple models and these three more complex models. There exists within UniSim and within HySys and within a great deal of other process simulators the ability to program your own chemical reactions as well. That is not something we're going to be covering in these tutorials, but again, it's a capability that you need to know exists. Okay, so the simple rate model, the kinetic model and the heterogeneous catalytic model must be used with the correct type of reactor, and the correct type of reactor model is either the continuous stirred tank reactor model, the CSTR model, or the plug flow reactor model. Both of these reactor models will give you design information for a unit, and so therefore they need to have the detailed kinetic data in order to yield that. Note as well that both the CSTR model and the plug flow reactor model can also be used for dynamic simulation too. So, we've set up the simulation environment. The simulation environment consists of defining chemical species, defining the thermodynamic model, and defining the chemical reactions. Once we've done that, we can then move into creating the flowsheet at the appropriate level of detail. Graphically within UniSim and HySys, this is a different screen and you're presented with different tools, and it is visually segregated from that first step, setting up the simulation environment. So if we think about flowsheet development, again what we're going to see is that a number of different approaches can exist for modelling a given unit, and again the choice of the approach that you use depends on the aim of your simulation. Don't forget that the aim of these tutorials is that basic flowsheet development, and so that's the context within which we're going to look at the unit models. So here on the whiteboard I've put up two examples of a simple unit model. They can change the temperature of a material stream. So for example, a cooler will cool a material stream down and a heater will heat a material stream up. All that you need to know for this is either what the target temperature is. You might just specify T2 and the simulator will work out what energy requirement is. Or you might have a given amount of energy to heat and cool a stream by, so you might specify the energy and it will backwork the temperature for you. Effectively, all that's going on here is a calculation of your energy. E is going to be your mass flow rate, m dot, times the specific heat capacity, Cp, times the temperature difference, T1 minus T2. This is a good model to use for flowsheet development because you're not worrying about the detailed mechanical design of the heat exchanger. That's a level of detail that's not relevant at this point. However, if you do want to worry about the level of mechanical design, then there are other models that you can use. There's a shell and tube heat exchanger model, which will give you the full design data, including tube pitch, tube spacing, total tube area, various estimates of how the baffling of your shell side can affect your heat transfer coefficient, and so on and so forth. And there's a model called the multi-stream heat exchanger, which is very, very useful, for example, if you have one hot utility heating up multiple cold utilities, as can often be found within refrigeration systems. Again, this tool yields the full design of your heat exchanger. If you look at the palette within UniSim or HySys, you'll see that there are a lot of other heat exchange unit operations as well. For example, you've got fired heaters, you've got cooling towers, all of which are detailed unit models. So, for the tutorial, we're just going to be looking at heaters and coolers because all we're concerned with is heating and cooling a stream up or down, and we're not bothered about the full mechanical design of the unit that achieves that at this stage. You'll see that this philosophy of having different tools to do the same job in different levels of detail is carried forth into all sorts of other unit operations as well. I'll give you an example now of some separation operations. So the simplest separation operation is a component splitter. What a component splitter is doing is simply saying send 100% of A to the top of this particular column and 100% of B and C to the bottom. It's not worrying about how it's done. It's not worrying about number of trays or theoretical stages or reflux ratios or anything of that nature. It's just saying A goes to the top, B and C goes to the bottom, which has a number of uses. It can assume that you can design a distillation sequence to that, and you can leave the distillation sequence design out of the flow sheet for the time being, but have the result of it within the flow sheet. Sometimes it can also be very useful as well for making subtle corrections within a more detailed flow sheet. Sometimes you'll see that, for example, you can get traces of non-condensable gases left over after certain separation operations, for example, flash separation. You might have a very fractional level of dissolved hydrogen in a liquid stream, which is an artifact of the prediction of the thermodynamic model. But as soon as you put that stream into a distillation column and specify a total condenser, it will try and condense out the hydrogen, which means that your total condenser goes down to minus 270 goodness knows what degrees C, which of course is completely unrealistic. And so a component splitter preceding that distillation column can just in effect clean up the feed to that column by saying, look, get rid of all the hydrogen. We know it's an artifact of the thermodynamics and not real, but what we want to be able to do is not have that dissolved condensable gas affecting downstream unit operations. So component splitters have a number of uses depending again what it is you're trying to do. If you're worried about distillation itself, then as we'll see in the second tutorial, there's a defined sequence to how you model distillation. The first tool that you use is a shortcut column. This is basically saying use Fensk, Underwood and various other equations, simplified binary or multi-component equations, to figure out what a rough reflux ratio and what a rough stage count would be for this unit operation given the components and given the thermodynamics. You then take that data and do a second stage of modelling, which involves what's termed a rigorous distillation column. Within this tool, all the complete heat and mass balances are being solved theoretical stage to theoretical stage, and you're actually getting a prediction of what a distillation column would physically do under those conditions. So again, 3 different tools that can perform very, very similar tasks, but in very, very different ways, requiring different levels of information to start and giving different levels of information when they complete and successfully run. So let's recap a few key points. First of all, most importantly, understand your aim. What are you trying to achieve with a simulation? Secondly, use reactions and models appropriate to your aim. Don't over-design. Also, don't under-design. Third, really importantly, validate your thermodynamic model. An unvalidated thermodynamic model can wreck a simulation and render all the hard work and time that you've invested in making it absolutely pointless. Fourth, don't forget to follow the simulation workflow. Define your components, define the thermodynamics, define the reactions, and then build up your flow sheet.